Okay, so what we want to do now, we know what simple domains are, and we want to see how we calculate double integrals on simple domains, and it's going to be via iterated integrals, just like we did on rectangles. So let me remind you what the theorem was for rectangles. So this is the theorem that we already know, and we already demonstrated in an example. If D is a rectangle, which we denoted by AB cross CD, if D is a rectangle, and the easiest version is assuming that F is continuous on D, then the double integral on D of fxy dx dy can be calculated as an iterated integral, as the integral from a to b dx of the function of x, which is the integral from c to d dy of fxy. So everything inside here, x is a parameter. So this thing is a number which depends on x. A number which depends on x is a different way of saying a function of x. So this inner part, everything in the parentheses here, is a function of x, and we're integrating it with respect to x. Okay, so this everybody knows already. Okay, now we want to generalize it for the situation where D is not necessarily a rectangle, and the extent to which we can generalize it is when D is what we called a simple domain. Remember what a simple domain was? X's between a and b, y's between two functions of x. Or vice versa, y's between c and d, x's between two functions of y. Okay? So here's the generalization of this theorem. So here's the generalized theorem. Let fxy be defined on a simple domain D. Again, one can write an easier version. The easier version would be to assume that f is continuous. But f may be not necessarily continuous. It can satisfy some weaker assumptions of integrability, okay? Namely, that all the integrals that are going to appear here exist, okay? That's the meaning of being integrable. In order to make life simple, I'm going to state it for continuous functions, okay? Assume f is continuous on D. When a function is continuous, it's always integrable. Okay? Then, the double integral on the domain D of fxy dx dy equals, and now I'm going to do kind of what I did previously, except, so the outer integral is again going to be an integral between a and b dx, because the domain, all the x's are restricted between a and b, right? But now the inner integral dy is going to be an integral from y equals y1 of x to y equals y2 of x dy of fxy. Okay, so let me just quickly jot down the domain here. This is a bird's eye view of the domain of the function. The domain now is x's between a and b, and y's between some two functions, y1 of x and y2 of x. And we indicated this by, so the domain is this thing inside here, but I want to shade it in a suggestive way which will help us in thinking of these problems and calculating later. So this is D. Okay, x's are restricted between a and b, and for each x, the y's are between two functions of x. So this corresponds to this picture of the domain. Clear? Where's the graph of the function in this picture? Where's the graph of fxy? Exactly. Exactly. Okay, so people were doing it in various ways, but everybody was hinting that it's somewhere here. Okay? Some people were doing like this, and some people were doing like that. Okay. Good, everybody? Okay. So what I want to do is the following. So before I do it, so again, there's a stronger statement which replaces this strong assumption of continuity by weaker assumptions, and still getting this result. And the assumptions are that this inner integral exists. Of course, if f is continuous, it does, but it can exist even if it's not. Okay? And that this integral exists. And then they're equal and one can be calculated by means of the other. Okay? Another remark is that, of course, this statement can be rephrased for a simple domain with respect to the other axis. Okay? So if it's simple this way, then we would have the outer integral. Maybe let's write that. Let's not be lazy. Remark for a domain of the form, y's between c and d, and x's between two functions of y, so x1 of y and x2 of y, and now the domain is this shaded area, again suggestively shaded like this. For d's like this, the statement of the theorem, we have that the double integral of f on d would be the integral between c and d dy of the integral between x equals x1 of y to x equals x2 of y dx of fxy. Clear? 1 second. So what I want to do is first illustrate an idea of the proof of this thing. Okay? And it's going to be based on the rectangular version, on the simpler version, which we didn't prove. I just kind of said what the idea is. The idea is looking at the baby version, at the one on the rectangle, looking at the Riemann sums and summing them once like this and then like this. Okay, once with respect to I and then with respect to j. I didn't put in the details. I just said the idea. Here I want to discuss the proof in a bit more detail because there's a point to be made there. There's something to learn, which does not go deep down into the Riemann sums. So that I want to do, and I want to do examples, of course. Okay? Question, yeah?
What is the directionality of the arrows?
The directions I put here on the arrows when I shaded it just means that for every fixed y, the x's are allowed to range between this function, all the way to this function. Okay? It's just illustrating what I'm thinking when I think of this domain. There's no timeline here. Okay, this point doesn't come in any sense before this point. Okay, I'm just thinking about it like this, and we'll see in examples how this helps me. This helps me identify simple domains and express if they're simple like this or like the other way. Okay, that we'll see in examples in a minute. Okay. Okay, so examples are going to be in the next clip, because there are quite a few of them that I want to discuss. Let's outline the idea of the proof of this theorem. I'm going to outline the proof for the previous situation, for this situation. So I want to show that the double integral equals the iterated integral, where the outer integral, the x's are fixed between two numbers, and the y's for each x are allowed to range between two functions. Okay, so I want to prove it, and I'm going to base the proof, walk with me one more board back, on the baby version for the rectangle, okay, which we are going to accept as true. Okay, so here comes the proof. So idea of proof. Here's the idea. So here's our domain. We're assuming that the domain is of this form. X's are restricted between A and B. And the y's lie between two functions. Here's one function. This we called y1 of x. And here's the other function, y2 of x. Right? And the domain is everything inside. Do you agree? I want to make a rectangle here, make a rectangle out of this thing, and I want to do it the following way. I'm going to look at the minimal value of y1, call that C. So that's the minimum of y1, and the maximum of y2, and call that D. So this is the y-axis. Okay? So the domain we're interested in is this thing inside. That's our domain. That's D. And it lives inside a slightly, I don't know about slightly, a bigger rectangle of the form AB times CD, where C is the minimum of y1 and D is the maximum of y2. Everything is continuous here, so we're assuming that minima and maxima exist. Okay, 1 second. Let me express the full idea. Okay, and I want to define a new function as well. So remember that we have fxy, which all we know of a priori is that it's continuous on D. D is the inside here. We know that fxy is continuous on D. As far as we know, it may not even be defined outside of D. Okay, I want to define a new function. Define, let's call it g of xy. It's going to be exactly the same as fxy in D. And it's going to be, I don't have enough space here. I'm going to move this a bit. Define gxy equals fxy whenever xy is a point in D. So I'm not changing f at all on the domain which I was interested in the first place. And I'm going to define it to be 0 outside of D. Okay? And in particular, it's going to be 0 in this rectangle on all points which are not inside D. Okay? Is it clear what G is? Okay? Now here's a little trick, well, not a trick, a little delicate point to pay attention to. Is G continuous? Why are you doing this? Well, because you think it's not. Why not?
Because it could jump from a hypothetical value.
Right. It's some value up here above D, right? The graph lives here. It's some value above D, and then it has these very steep cliffs that drop to 0 outside. Okay, so if we take the picture and rotate it so it looks, so we look at it in perspective, F is defined somewhere on D, and then G is 0 outside. So it's this big, think of, do you know Monument Valley in the United States? So somewhere between Utah and Arizona, there's this beautiful area that appears in Western movies, like cowboys and stuff, where you have these mountains, that are like, that are very steep, that they look like G, like the graph of G, almost. Well, they look things that look like this. They really look kind of like this. Well, G is even more Monument Valley-ish. So the graph of G is something like this. This was the graph of F defined over D, and then the graph of G is just 0 outside. 0 on everywhere else. Okay, so the graph of g is 0, and then the graph of f up here. Do you agree? Does everybody see the picture? Do you understand why I'm saying that that's what the graph... So g is not continuous, right? It has these crazy jumps. Okay, so g is not continuous. Nevertheless, I want to use the baby version of the theorem on iterated integrals on g. And I didn't state it because I only assume, that that baby version works for continuous functions, but I said that it can be generalized, and I'm going to use it, the generalization. Okay, so I'm confessing about a little cheating that's going on here in the background. But the idea is what's important. That's why I wrote the idea of the proof. Okay. So I want to calculate the double integral, and I'm going to be a bit sloppy intentionally so we can see things without too many xy's, dx, dy's. I want to calculate the integral of f over d. That's what I was originally interested in, right? Do you agree that the integral of f on d equals the integral of g on r, where r is this rectangle? R is now AB times CD. R is this entire rectangle. The integral of f on d is the same as the integral of g on the bigger rectangle, because I'm adding volumes under the graph of g, but g is the zero function outside, so it contributes nothing. Do you agree to this? Everybody? Clear? Okay. Now this I know how to calculate. This is the integral of a function over a rectangle. I can do it using iterated integrals. The integral from a to b dx of the integral from c to d dy of g. This is by the baby version of the theorem. Integrating a function on a rectangle. Good? Everybody? Okay. Now let's look at the inner integral. The inner integral is the integral of g. X is now fixed, right? X is a dummy variable. It's the integral of g x y from c to d dy, right? I'm thinking of x as a parameter when I'm doing the integral dy here, y ranging between c and d. Do you agree? So now I'm looking at, maybe let's just bold it. I'm looking at a specific x, maybe this x, and I'm integrating just from here to here, all the way. Let's zoom in on this picture a bit. I'm fixing an x. I'm zooming in on this. Let's take another color. I'm going to draw this part here, make it bigger. Here it is. I fixed an x. Here's that fixed x. Here's the value c. Here's the value d. Here's the graph of y1, somewhere here. And here's the graph of y2, somewhere here. And I'm integrating for this fixed x, I'm integrating g of y between c and d. I'm integrating from here to here, from c to d. This is c and d, and this is y1 of x, and this is y2 of x. Do you agree? Okay? Integrating from c to d, the function g. But what is this integral? I can write it, and you should all the times be thinking of doing this and thinking of integrating like this. Okay, the graph of the function is up here. Do you agree? The graph of f is up here. This is a bird's eye view just on the domain. Whoever is looking at me and thinking, what is he talking about? What does he mean a bird's eye view? What is the graph of the function is up there? That's crucial for understanding everything we do in this course. Okay, if that's a point you missed at any time, crucial to go back and understand that point. Okay, if you're actually sitting here, you can come to me and I'll be happy to explain it again over the break, but it's crucial to understand this. Why am I saying that the function is up here and this is just the domain? Okay? We discussed it when we discussed graphs of two variable functions. Okay, so do you agree that I can rewrite this as the outer integral I'm not touching, the integral from a to b dx, I'm leaving that untouched, but inside I'm going to break it to, I'm going to integrate from c to y1 plus integrate from y1 to y2 plus integrate from y2 to d. Do you agree? That's the same as integrating all the way from c to d. So I'm going to integrate from c to y1 of x, integrate g, plus integrate from y1 of x to y2 of x, g, plus integrate from y2 of x to d of g, and all these integrals are dy. Okay, this is very sloppy writing, but I want to emphasize the ideas here. And I'm thinking of g as a function of y alone. X is fixed. I'm later going to integrate dx. Do you agree? Okay. But what is this thing? What's the integral from c to y1 of g? It's 0. G is the function 0 over here. It's outside of the domain D. It's down here. It's 0. G is 0 whenever we're outside of D. So this integral contributes nothing. This thing, this integral, is 0. Do you agree? Same goes from here. From y2 to d, I'm integrating the function 0. G is 0 outside of d. D is inside here. Do you agree? So this integral also contributes 0. Right? So what I'm getting is just the integral from y1 to y2 of g. Do you agree? But what was g between y1 and y2? It coincides with f. So I can write here, instead of g, I can write f. And that's precisely the formula I was trying to prove. So this equals the integral from a to b dx of the integral from y1 of x to y2 of x dy of gxy, which is the same as fxy in this domain. So the double integral of f on d equals the iterated integral as the theorem asserts. Clear? So the idea here is important. We kind of used a similar idea when we defined double integrals on domains which were not rectangles. Remember, we did something very similar. You should start to pick up this idea as something general, as breaking the domain and looking at, okay. Questions on this? Yes?
I wanted to ask if D and C are like the maximum of the function y, or like in the
D
domain?
is the maximum of the upper function.
But in the domain, or like in general?
Only between A and B,
Only.
right? I don't, for all I care, y is not defined outside of A and B. Okay, I'm only interested in what's going on between A and B. Yes?
For iterated integrals, does it matter which one you put on the outside and on the inside?
If we're looking at a rectangle, it doesn't matter, right? In this situation, when we're looking at a rectangle, it doesn't matter which one is the outer one and which one is the inner one, okay? If we're looking at a situation like this, a simple domain, it does matter, okay? And I'll give you a quick answer in terms of a little picture, okay? But we're going to discuss it in a couple of clips. We're going to discuss the issue, which is an issue that is important, of changing the order of integration, okay? And that's where it's going to show up. But just to quickly answer your question, let's look maybe at this picture here. So here, the y's are between C and D, the x's are between two functions, x1 and x2. Okay? So if I want to cover all the points in this domain, I can allow the y's to range between c and d. For each fixed y, the x's are going to go along these arrows. Do you agree? This domain that's drawn here is not simple with respect to the other variable. I cannot say that I can fix the x's between a and b, whatever you want a and b to be, and then allow the y's to range, because I won't be doing something simple. For example, at this x here, I would be going, well, not a good example of an x. Maybe at this, not a good example of a domain, but tricky. The point is that there are going to be x's, if I try to restrict between here and here, there are going to be x's where I enter the domain, go out again, and enter it again. Okay, it's kind of hard to see here. I have to make it a bit more grotesque in order for you to allow me to do something like this. Okay, I didn't do a major change, but then at this x here, you would be integrating, entering the domain, here we go, leaving the domain, and entering it again up here. Do you see that? And that's not a simple domain. The y's for this given x don't live strictly between two functions. Okay? They're between this function and then again between this function and the top. Do you see that? Okay? So it's not true that you can just flip the order, and this one on this domain, whenever you have a situation like this, where this is not a graph of a function, you can't calculate using the iterated integral the other way. It only works for this way. Okay? When the domain allows you to do both, when it's simple in this direction as well as simple in this direction, then you can do change of order of integration, and that we're going to discuss, how to do it precisely. Okay? It even has a name. It's called Fubini's theorem. We'll discuss it. Okay? Last question.
How can it be that when we talked about limits, then you said iterated limits was a big no-no, but now when you talk double integral, it's okay, because last time you also said it's a form of a limit.
Right. That's a good question, and the answer is that it's a theorem, and the theorem has a proof, and we never... Okay, so this baby theorem, which we based all our discussion on, has a proof. I outlined the idea, but I never did the formal proof. And the proof says that, yes, it is okay to do iterated integrals. It's a theorem. It works. Okay? Whereas, via examples, we saw that the notion of iterated limits in general is, as you said, a big no-no. Okay? So it's not true that the limit of fxy is fix x, take the limit in y, and then take the limit in x. That's, in general, not true. Okay? Specific theorems tell you that in some instances you can change the order of integrals, for example, which are limits of Riemann sums. For example, in this case. And you've seen other examples. You've seen, for example, in Calc 1, you did term-by-term integration of power series. Okay, or term-by-term differentiation of power series. That's changing the order of infinite summation, which is a limit, and the derivative, which is again a limit. Okay, so there are situations where changing orders of limits are kosher, are okay, but those are theorems. You have to prove them. Okay, and in general, it's not true. That was the big no-no when we discussed limits in general. Okay? Okay, so I think it's always a better idea before we continue, if you have more questions, postpone them until we do examples. Let's look at some examples, see how this works. I think things become much clearer instead of just talking abstractly. So that's going to be in the next clip.